Everything we see, the stars, galaxies, even the space between them, could one day shrink back together like a cosmic reverse explosion. This is the big crunch. Instead of the universe stretching forever, it stops, turns around, and collapses under its own pull. Think of it like a balloon you blow up at a birthday party. If the air keeps flowing, the balloon grows. If the flow stops and you squeeze, it shrinks back down. Or imagine tossing confetti into a gusty day. If the wind dies, gravity drags every piece back to the ground. In the universe's case, gravity is the hand, and mysterious forces like dark energy are the wind that might keep things expanding. Why watch? Because this idea tells us about the tug-of-war that decides the universe's fate. In plain terms, you'll learn what would happen to galaxies, stars, and even time itself if a collapse began, how scientists would spot the first signs, and how likely this ending really is, plus a few surprising everyday comparisons and a little cosmic humor, not the breakfast kind of crunch. The Big Crunch in a nutshell. Astronomers see that space is stretching and galaxies are moving away from each other, and one possible outcome if that stretching slowed and reversed would be a gradual shrinking of the cosmos until everything came back together. Right now the push that makes space expand faster is called dark energy, a mysterious effect that acts like a gentle shove in all directions. If that shove weakened or flipped, gravity from all the matter in the universe could begin to win, pulling things inward instead of letting them drift apart. If gravity takes over, the process would start big and slow and then speed up. Galaxies that are currently separating would stop their outward drift, then drift inward toward one another. Picture neighborhoods slowly moving closer until entire cities bump into each other, collisions between galaxies would become common, and star systems would be jostled out of their tidy orbits. It's like a crowded dance floor that gradually compresses until everyone is forced into a tight huddle, awkward, loud, and full of consequences. As the collapse continued, conditions would get more extreme, stars would collide and be torn apart, black holes would merge into ever larger monsters, and temperatures would climb. At some point atoms themselves could be stripped down by intense heat and pressure, leaving a soup of particles and radiation. Think of heating a pot on a stove. The contents change as the temperature rises, only in this case the pot is the entire universe and the heat never stops climbing. What happens at the very end is still a question for physicists. One outcome could be a state of incredibly high density and temperature where our current physics breaks down, something we don't fully understand. Another idea is that the collapse might rebound into a new expansion, bounce, that starts another cycle. Observations today show the universe's expansion is speeding up, which makes a full-scale collapse seem unlikely under present conditions, but if the properties of dark energy changed, the story could be different. Either way, the Big Crunch is a useful way to explore how cosmic forces like gravity and dark energy compete, and it gives a dramatic, if somewhat inconvenient, picture of an ending that would certainly make scheduling a picnic in space look foolish. A short history of cosmic fate theories. People have long debated whether the universe will keep stretching out forever or someday turn back and pinch itself into a compact ball. Early thinkers and later scientists offered a handful of big-picture ideas to answer that question, each one shaped by the best observations and guesses of its time. Some proposals pictured an endless, ever-expanding cosmos, others imagined a universe that would slow, stop, and fall back in on itself, and a few suggested rhythmic cycles of birth, death, and rebirth on a cosmic scale. One simple way people described expansion looks like a loaf of raisin bread rising in the oven. Raisins move away from each other as dough puffs up, and space itself can behave the same way. If the push of expansion is stronger than gravity's pull, the loaf keeps expanding and the raisins never come back together. That's the idea behind an ever-expanding universe. On the other hand, if gravity could eventually win, if there were enough stuff pulling inward, the dough would stop rising and might even collapse, squashing the raisins back together. That's the basic picture of a collapse scenario often called the Big Crunch. Scientists introduced alternatives along the way. The steady-state idea imagined matter appearing continuously so the universe looks the same at all times. Think of a crowd at a party where new guests quietly slip in as others leave, keeping the room full, only this one eventually lost support because observations showed clear changes over time. Another concept is the cyclic or oscillating universe, which is like a cosmic yo-yo or a bouncy ball that keeps bouncing, expansion, collapse, and bounce again. It sounds neat, like a sequel that never ends, but it runs into thorny issues when you try to explain how entropy, disorder, doesn't build up forever. Later refinements brought in the discovery that the universe's expansion is speeding up, not slowing, which changed the favor toward long-lived futures. This led to ideas such as a slow fade into heat death, where energy becomes evenly spread and no useful work can be done, like a party where everyone's asleep on the couch and the snacks are gone. Another wild possibility is the Big Rip, where accelerating expansion eventually tears galaxies, stars, and atoms apart. Picture a rubber band stretched so hard it snaps into nothingness, only far messier and with more screaming subatomic particles. Through all these shifts, the common thread is simple: our best models depend on what the universe contains and how strong gravity and expansion forces are. Observations, measuring how galaxies move and how light behaves across space, refine the options. So the story of cosmic fate theories reads like a detective tale, with hypotheses proposed, tested, discarded or revised, and sometimes revived in new forms. It's a human process, messy and creative, and occasionally funny if you think about physicists arguing whether the universe will be a forever expanding loaf or a dramatic cosmic belly flop. How gravity could turn the tables. Gravity could steadily gain the upper hand if the thing pushing galaxies apart, a mysterious pressure scientists call dark energy, weakens or changes behavior. Dark energy is the name for whatever makes the universe's expansion speed up. Think of it as a gentle force that keeps the cosmic fabric stretching. If that gentle push fades, then the universal tug from every lump of matter starts to matter more, and gravity's cumulative pull could slow the expansion, stop it, and then pull everything back inward. A useful everyday picture: a balloon you stop inflating will stop expanding and might sag. On cosmic scales, if the source of inflation fades, gravity can take over. As distances between galaxies shrink, gravity doesn't stay static, it grows stronger because things are closer together. Galaxies begin to interact more, and collisions become common. We already see galaxies crashing into one another in the universe today. In a collapsing scenario, those encounters would only increase, turning isolated islands of stars into chaotic, merging systems. At the centers of many galaxies sit black holes. As their host galaxies merge, those central black holes can meet and combine, producing powerful bursts of energy and those spacetime ripples we call gravitational waves, the same type of waves astronomers have detected from black hole collisions. Closer to home, stronger gravity makes things squeeze and stretch in uneven ways. When two regions pull at different strengths, objects get tidally stretched, a bit like pulling apart a strip of taffy between your fingers. On the largest scales, whole clusters of galaxies would compact, heating gas and smashing stars together. Collisions between stars can ignite furious bursts of radiation, and material falling into growing black holes gets heated to blistering temperatures, glowing brightly before it disappears. The energy budget shifts from peaceful expansion to intense heating, pockets of matter become denser, and light struggles to escape. What happens next depends on physics we don't fully understand yet. One possibility is that everything collapses into extremely dense states where our usual rules break down, a bit like trying to use a map when you've driven off the road, it no longer applies. Another possibility, posited in some ideas, is a rebound or bounce, where collapse triggers a new expansion. No conclusive proof favors one outcome today. Either way, gravity's role is straightforward to grasp. It's the universal pull that, given the chance, turns slow separation into a dramatic reunion, and that reunion gets messier and hotter the closer and more crowded things become, a cosmic party that ends with everyone pressed up against the snack table. Dark energy, the cosmic spoiler. The thing pushing galaxies apart faster than they should be is called dark energy, and it acts like a mysterious outward shove built into space itself. Astronomers estimate it makes up about 70% of the universe's total energy budget, so it's not a background whisper, it's the loud roommate of the cosmos rearranging the furniture. Picture a balloon being gently inflated, dark energy is the steady breath that keeps the surface stretching, while gravity is the stubborn rubber that wants to pull things back together. Both are acting at once, and the balance between them decides whether the universe keeps stretching or someday turns inward. If dark energy behaves like a constant push, the universe will keep expanding faster and faster, and a big collapse becomes very unlikely. On the other hand, if this push weakens or flips sign, gravity could gain the upper hand and bring everything back in, a cosmic retracing of steps. Think of it as a tug-of-war where one team suddenly gets tired. If the dark energy side tires, the gravity team can win and haul the universe inward. Short sentence: balance is everything. Current observations are consistent with dark energy acting like a simple, steady pressure built into space, what scientists often call a cosmological constant, but they do not prove it beyond doubt. Astronomers check this by measuring how far and how fast distant supernovae appear, mapping where galaxies cluster, and studying the faint afterglow of the early universe. Those are fancy tools, but the idea is plain: measure expansion today, measure it over time, and see if the push changes. If it does change, even slightly, the future of the cosmos could be very different. For everyday life, dark energy is mostly a headline-worthy curiosity. It won't affect your morning commute. Yet its behavior decides whether the universe coasts forever, tears itself apart, or eventually collapses in a dramatic return. Scientists keep refining measurements because knowing whether the cosmic push is constant or fickle tells us the endgame. A little cosmic humility helps. Humorously put, dark energy is the ultimate party spoiler. It determines whether the universe keeps the music playing or pulls the plug. From expansion to contraction, trigger mechanisms. Astronomical observations show that space is, at the moment, stretching faster and faster, and whatever flips that trend must either cut the mysterious outward push or crank up the inward pull. Something has to overcome that steady acceleration for the whole cosmic expansion to slow, stop, and turn around. This is not magic. It's a change in the balance of forces acting on everything from galaxies down to dust grains. One plausible trigger is that the thing doing the pushing, often called dark energy, could itself change. Think of dark energy like a slowly moving breeze that has been inflating a balloon. If the breeze calms or reverses, the balloon can sag. In physics terms, the property of this energy might vary with time, and if it dwindles or becomes attractive instead of repulsive, the expansion would decelerate and then reverse. A household example: a thermostat that slowly shifts from keep warm to start cooling, and suddenly the house contracts metaphorically. Follow along, no remodeling required. Another route to contraction involves a sudden change in the nature of empty space, known as a vacuum phase transition. Picture a marble sitting in a shallow dip on a tabletop. If the table tip or the dip shape changes, the marble can roll into a deeper valley and release energy as it does so. In cosmic terms, a region of space could switch to a lower energy state, and that new state might prefer a universe that collapses rather than expands. The change would likely spread outward as a bubble, sweeping through space like a spreading freeze that turns supercooled water into ice, dramatic and noisy on cosmic scales, though we do not have a popcorn maker for universes. A different possibility is that the rules governing gravity could be subtly different on the largest scales than they are near Earth. If gravity becomes effectively stronger across vast distances, the mutual pull between galaxies could win over the outward push and pull everything back. Imagine a rubber band that stiffens as you stretch it. At first it yields, but later it snaps back with more force. Theories that add new ingredients, extra dimensions or unfamiliar particles, can produce that effect, but these ideas are speculative and would require evidence beyond our local observations. Collisions or interactions with other large-scale regions could also act as a trigger. Some theoretical pictures of the cosmos allow for neighboring bubbles with different properties. If one such bubble intruded on ours, it might change the energy balance and force a collapse. This is the cosmic equivalent of two crowds bumping into each other and changing the flow. It's a dramatic scenario and not something anyone recommends for a peaceful universe. Right now, measurements favor continued expansion, so none of these triggers have been observed in action. Still, The mechanisms are grounded in real physics and have clear analogies in everyday life: a breeze changing direction, a marble finding a deeper dip, a rubber band stiffening, or crowds colliding. That keeps the Big Crunch idea in the realm of plausible outcomes, even if it remains a long-shot prospect, and if the universe did decide to take the scenic route back to a point, it would be because one of these tidy trigger mechanisms finally flipped the switch. Critical density and the fate of the universe. The balance between how fast space is stretching and how much stuff it contains decides a lot about the universe's future. Call that, how much stuff, the average mass and energy packed into space. Scientists compare it to a special threshold called the critical density. If the universe has more than that threshold, gravity would eventually win and pull everything back together. If it has less, the outward pull of the initial expansion would carry galaxies apart forever. Simple in idea, but reality adds a few twists. A helpful everyday picture is throwing a ball straight up. Throw it too softly and it falls back. That's like a universe with more than the critical amount of stuff, a future collapse. Throw it hard enough and the ball escapes Earth's gravity and never returns. That's like an underweight universe that keeps expanding. Throw it just at the right speed and it keeps going but slows down forever. The right density is similar. When the actual density matches the critical density, the geometry of space is flat and the cosmic expansion just asymptotically slows without a dramatic recollapse. Think of escape velocity, but for the whole cosmos. What counts as stuff is more than the atoms in stars and gas. Ordinary matter is only one ingredient. Dark matter adds unseen mass that tugs gravitationally, and radiation contributes very little now. Then there's dark energy, a mysterious effect that pushes space to expand faster instead of slowing down. Because of that push, knowing only the average density isn't enough to predict the endgame. In the simplest models where dark energy doesn't exist, the density relative to the critical value neatly divides eventual recollapse from eternal expansion. Add dark energy, and a universe that looks heavy might still keep stretching forever. It's like packing a suitcase. You can add more clothes, but if the suitcase suddenly grows a motor and starts ejecting items, the weight alone won't tell you whether it stays closed. Astronomers check this balance with real observations. They study the glow leftover from the early hot phase of the universe, map how galaxies cluster, and measure how bright exploding stars appear at great distances. Those different probes together show that the total amount of mass energy sits very close to the critical threshold that marks flat geometry. That doesn't mean the cosmos will crunch, rather, it tells us about the universe's shape and the competing roles of gravity and whatever is causing accelerated expansion. So unless dark energy decides to go on a cosmic diet or gravity gets unexpectedly stronger, a dramatic big crunch seems unlikely. Still, the balance between expansion speed and how heavy the universe is remains one of the clearest, most intuitive ways to think about the universe's fate, like checking whether your backpack is light enough to make the hike or heavy enough to force you back home. The role of dark matter in a collapse. Astronomers find that most of the matter in the universe does not shine. This unseen stuff is called dark matter, and we know it exists because it tugs on things with gravity. Galaxies spin faster than the visible stars can explain, and light bends around mass that we cannot see. Think of dark matter as invisible passengers on a trampoline. You can't see them, but the trampoline sags more than it should, and anyone jumping will feel the extra pull. That extra pull matters a lot if the universe ever starts to fall back in on itself. Whether space keeps stretching or eventually turns around depends on how much total weight there is everywhere. Dark matter adds to that weight. If other effects that push the universe apart were to weaken, the gravity from dark matter would help slow expansion and could speed up a collapse. Picture a crowded hilltop where more people gather at the edge. One more push from the crowd and the whole group might roll down. Dark matter behaves differently from the stuff we are made of. Ordinary matter can collide, rub, heat up and then cool by shedding energy as light, like a hot pan cooling on a kitchen counter. Dark matter does not do that. It does not glow, stick, or lose heat the way gas and dust do. During a collapse, ordinary matter can fall into tighter clumps because it can cool and settle, while dark matter tends to stay in broader, ghostly halos. The result is not a smooth squeeze but a lumpy one. Dark matter makes the landscape of collapse uneven, creating deep wells where galaxies and black holes will form first. It's a bit like making cookie dough with chocolate chips. The chips, dark matter, create spots that bake differently. Local behavior changes the global picture too. Since dark matter seeds the formation of galaxies and clusters, those already deep pits of gravity would become the first places to crunch. In collisions, dark matter often sails through where gas slows and piles up, so during a universal contraction it could keep pulling distant regions inward with less friction. We still do not know what dark matter particles are, and that uncertainty affects the details. If dark matter clumps at tiny scales or stays smooth will change how sharply structures collapse. But whatever its microscopic nature, dark matter would act like a massive, invisible scaffold during a big crunch, rearranging where and how things fall, and making the collapse more of a messy, lumpy reunion than a neat, uniform squeeze. In short, dark matter would be the quiet stage manager tugging on all the curtains while the visible actors try to make sense of the script. Cosmic timeline: how fast could it happen? Current observations tell us the universe is speeding up its expansion, which makes a collapse less likely under what we know now. Think of space itself as a stretchy fabric being pulled outward. The speed at which that pulling happens is a key number scientists track. If that outward push weakens or reverses, gravity could eventually take over and the expansion would slow, stop, and then turn into contraction. How long that would take depends on the balance between the outward push, called dark energy, and the pull of matter and radiation. If dark energy stays steady and repulsive, collapse won't happen. If it gradually fades, the turnaround could be extremely slow, so slow that many generations of stars and galaxies would live and die before anything serious changes. If dark energy suddenly changed sign or strength, the shift could be much faster on cosmic scales, like a car suddenly switching from cruise control to full braking. But even fast, in this context usually means time spans far beyond human lifetimes. During the slow version, galaxies would coast away for a long time before the expansion finally stalls. Bound systems like galaxies, and even solar systems, would resist the first stages of contraction because local gravity keeps them together. Picture a city left on a slowly shrinking island. The shoreline moves inward for a long time before the water reaches the town square. Later, as contraction intensifies, clusters of galaxies would start crashing together, temperatures would rise, and structures would be compressed. It's a cosmic traffic jam that starts subtle and then gets dramatic. In a rapid collapse scenario, the late stages accelerate quickly compared to earlier epochs. Distances between objects would shrink faster, collisions would become common, and the universe's temperature and density would climb. Still, quick here is relative. The short end of cosmic drama is still unimaginably long for a person. Scientists use models to translate different assumptions about dark energy and matter into possible timelines, but those models all hinge on what dark energy actually does next, which we can only infer, not decree. Observationally, the timetable is constrained by measurements of how the universe expands at different distances and directions. If future data showed signs that the outward push is weakening, models would shift toward collapse scenarios and give rougher estimates of how many cosmic seasons remain. Until then, talking about a big crunch is mostly an exercise in exploring possibilities. It's a useful thought experiment, though, like planning for a very slow, eventual pancakeification of the cosmos, amusing to imagine, and scientifically interesting, but not something to cancel your weekend plans over. Temperature and density on the way down. As the universe contracts, the amount of stuff packed into every cubic bit of space steadily rises, so temperature climbs along with density in a fairly predictable way. Think of a bicycle pump. When you push the handle down, the air inside gets squeezed and the pump feels warm in your hand. The same idea applies on the grandest scale. Matter that was once spread thin becomes tightly packed, and energy that used to be thinly spread as faint light or cold gas becomes concentrated and much hotter. Light itself changes during the fall. Photons, the little packets of light, get squeezed together and gain energy, so the glow that filled the cosmos becomes bluer and then much more energetic. It's like turning a dim room illuminated by a candle into a spot heated by a focused beam of sunlight. The color shifts and the heat goes up. As photons gain energy, they can knock electrons off atoms, so neutral atoms can't stay intact and the gas turns into a roiling soup of free nuclei and electrons, a state physicists call a plasma. In everyday terms, atoms get their furniture tossed out and become a noisy, freewheeling crowd. Collisions get relentless when density rises. Particles slam into one another so often that random motions turn into heat, and the gas can no longer cool itself effectively because emitted light gets reabsorbed quickly. This is similar to a crowded subway car. When too many people are packed in, nobody can move freely and things heat up, literally in the cosmic case. High temperatures also open up new kinds of reactions. Nuclei that once lived peacefully inside atoms can be smashed apart by energetic photons, and under certain conditions, energetic light can produce matter and antimatter pairs out of pure energy. It's a lot like overeating at a buffet and suddenly finding new dishes appearing, except far less tasty and more energetic. Gravity does more than pull, it converts stored gravitational energy into heat as structures squeeze together and fall inward. When huge clumps merge, they behave like kettles being stirred vigorously. Potential energy is turned into motion and then into thermal energy. In regions that are denser to begin with, this makes hot spots even hotter, producing strong local temperature differences rather than a perfectly smooth increase everywhere. Some areas could become so opaque that radiation is trapped, no longer streaming freely across space but steaming inside like a sealed pressure cooker. At the most extreme stage, temperatures and densities reach values where our usual descriptions of matter and light start to stretch thin and may no longer be fully reliable. That means predictions get tricky. Current theories point to unimaginably hot, dense conditions, but what exactly happens next is a frontier of physics. Scientists might need new ideas to describe those final moments. For the rest of us, it's enough to know that the universe collapsing would be like turning up a cosmic oven and cramming everything into the pan, messy, extremely hot, and not a place you'd want to set a picnic. Galaxy collisions and the last stars. Galaxies that were once separated by vast emptiness would begin moving closer together during a collapse, and collisions between them would become common. These encounters are not gentle overlaps. Vast clouds of gas slam into one another, stars pass by at dizzying speeds, and gravity reshuffles entire star systems. Think of two cities slowly drifting together until neighborhoods merge, roads get jammed and fireworks start, only on a scale so huge that rush hour lasts millions of years. When the gas in colliding galaxies is squeezed, it often lights up in a frenzy of new star birth. Pockets of gas collapse under their own weight and ignite into bright, massive stars that burn hot and fast. These new giants are spectacular, like stadium flares that outshine everything nearby, but they live fast and die young. After a short, brilliant life they explode as supernovae, scattering heavier elements and stirring the gas further, like a series of bonfires that briefly make the night visible before ashes fall. Smaller, cooler stars behave differently and matter a lot in the endgame. Low-mass stars, called red dwarfs, burn their fuel slowly and steadily. They are the marathon runners of the stellar world. While bright massive stars flare and vanish, red dwarfs can keep burning quietly for an incredibly long time, acting as the last persistent points of light when most others have gone dark. Dead stellar cores, white dwarfs, serve as faint embers, slowly cooling and fading, and failed stars like brown dwarfs stay dim and unlit, more like coals than blazing logs. Collisions also stir up violent motions. Tidal forces stretch galaxies into long streams of stars, and interactions can fling individual stars out into lonely regions between galaxies. Central black holes get fed during mergers, sometimes growing loud and active as they swallow gas and shine brightly. That feeding frenzy can outshine whole galaxies for a while. But if repeated collisions heat the gas enough or if the supply of cold gas is used up, the ability to form new stars dwindles. In simple terms, you can squeeze and light a sponge only so many times before there's nothing left to squeeze. In the final stages, the picture becomes a patchwork of fading lights and dark ruins. New star formation will slow or stop, leaving long-lived red dwarfs and cooling remnants as the last beacons, while many stars have already been hurled into deep darkness by gravitational slingshots. It's a cosmic cleanup where the bright, short-lived fireworks are gone, and only the slow-burning lamps remain, like a party that finally settles into a few people quietly polishing the cups while the DJ packs up. A little melancholy, a touch of cosmic humor, and a powerful reminder of how collisions can both create and extinguish stellar life. What happens to black holes in a crunch? If the universe began to shrink instead of expand, all of the loose structures we know, galaxies, stars, gas, would be pushed closer together, and the giant dark objects at galaxy centers would not be immune. Supermassive black holes already sit in the centers of most galaxies and weigh millions to billions of times as much as the Sun. When their surroundings get crowded, they get very hungry. Short sentence for emphasis. Collisions between galaxies would become common as space compacts, and when galaxies smash together, their central black holes tend to sink toward the merged center and pair up. Over time, those pairs lose energy and spiral inward, finally joining into a single, bigger black hole while sending out ripples in space, gravitational waves, that carry away some of the system's energy. Think of it like two whirlpools merging in a bathtub, messy, loud in a cosmic way, and impossible to get out of if you're in the water. Denser surroundings also mean more material to fall in. Gas, stars, and even other black holes would be dragged into the growing monsters, and their outer boundaries, the point of no return, around a black hole, would expand as mass piles on. A simple way to picture this is a vacuum cleaner in a very messy room. The more clutter there is nearby, the faster it clears out. Short punchline: black holes love a buffet. There is also a slow leak that acts in the opposite direction. Black holes emit an almost unimaginably tiny amount of radiation, a process that can make them lose mass over very, very long times. For large, astrophysical black holes, this effect is effectively negligible compared with the dramatic events of a collapsing cosmos. Tiny black holes, if they existed, would lose mass faster and could evaporate before being swallowed into something larger, much like small snowballs melting faster than a boulder-sized one, but astronomers have not confirmed such tiny examples in nature. Toward the very end, classical physics suggests everything would compress toward an extremely dense state. In that picture, the separate identities of individual black holes would blur as all matter and spacetime itself are crushed. Physicists hesitate to call this a settled outcome because a full theory that combines gravity and quantum effects is still missing, so exactly how a black hole's internal core behaves as the whole universe collapses remains an open question. Short sentence to remind: the details are messy. For practical thinking, in a contracting universe, black holes are expected to merge, grow by swallowing nearby material, and dominate the final dynamics rather than quietly evaporate away. They wouldn't be safe islands, instead they would be major players at the cosmic endgame, behaving like the biggest, greediest players at a cosmic potluck. The ultimate compression, singularities and beyond. If the expansion of the universe were to reverse and everything began falling inward, gravity would slowly pull galaxies, stars, and planets closer together until space itself became far more crowded. Temperatures and pressures would climb as matter gets squashed into smaller volumes. Putting the same amount of stuff into a tinier box makes it hotter, just like pumping air into a bicycle tire makes the pump warm in your hand. Over immense scales the effect is the same: more crowding, more heat, and a lot more energetic particles bumping into each other. At the heart of the collapse, the idea of a singularity appears, a place where density and curvature are predicted by current equations to become extremely large, so large that our usual physics stops giving sensible answers. This is not a precise number you can write on a receipt, it's a sign that the theories we use, like gravity's classical description, are being pushed beyond their limits. Think of it like trying to describe the pattern on a crumpled sheet of aluminum foil using a ruler. The tools don't match the mess. In everyday terms, atoms themselves would be crushed, electrons can be forced into protons to make neutrons, so matter becomes more compact, like squeezing a marshmallow until it's mostly sugar paste. That's what happens in the cores of the densest collapsed stars we know. matter gets rearranged in ways unfamiliar from normal life. As densities keep rising, known forms of matter likely give way to more exotic states. Neutron-rich matter is one step. Push harder and particle interactions change so profoundly that even the building blocks inside protons and neutrons could move freely in a hot, dense soup. Laboratory experiments with particle colliders recreate tiny droplets of such a soup, for instance, and those experiments show matter behaving very differently than a rock or a gas. Near a theoretical singularity, space and time themselves would no longer behave like the steady stage we're used to. Distances and the flow of time could lose the straightforward meaning they have now. Picture roads all converging to a single point where traffic becomes indistinguishable, measurements that made sense earlier suddenly don't. What comes after that is open and exciting in a frustrating way. Our best guesses use ideas that try to combine gravity with quantum behavior, but they don't yet give one clear picture everyone agrees on. Some proposals suggest the collapse could bounce, turning compression back into expansion, while others imply the formation of a new realm whose rules differ from ours. Those are not wild inventions but attempts to patch the mismatch between the very big and the very small. Scientists compare this to trying to read tiny print with a blurry magnifying glass. You need a better instrument to get a clear answer. Meanwhile, day-to-day examples still help. Crumpling paper can hide creases you can't easily smooth, and squeezing a rubber ball too far makes it change shape in ways that are hard to reverse. The universe at ultimate compression behaves like the extreme version of those things, only vastly stranger and far less forgiving of our intuition. Quantum gravity and the breakdown of physics. Physics as we know it splits into two rulebooks, one that explains how planets and galaxies move under gravity, and another that tells us how atoms and particles behave. These two rulebooks work beautifully on their own but use completely different languages. When everything is calm and not too dense, each gives reliable answers. Problems start when the universe becomes extremely compact and both have to be applied at once. Classical gravity equations predict that, during a collapse, densities and curvatures of space grow without bound, and the math spits out infinities. That's not a subtle disagreement, it's like a calculator trying to divide by zero. The result is nonsense. In practical terms, the assumptions behind those equations stop making sense. Tiny scales where quantum effects matter become important, and the smooth picture of space and time used by classical gravity begins to look pixelated, like a photo blown up until you can see individual squares. At the heart of the problem is the idea that there is a scale so small that our usual notions of distance and time lose their meaning. Physicists call this the regime where quantum gravity is needed. Think of trying to describe a grain of sand with a rule meant for measuring continents. The tools are simply wrong for the job. In everyday life, this is like using a road map to navigate inside a house, helpful for the general layout, useless for finding the light switch. Under those extreme conditions, spacetime itself is expected to become fuzzy or granular, and particles no longer act like points moving through a smooth stage. Several research approaches try to answer what that fuzziness looks like. One idea imagines fundamental strands that vibrate, with particles and forces emerging from their vibrations. It's a bit like different notes coming from the same violin strings. Another treats space as made of tiny, discrete pieces, similar to a woven fabric where each knot holds information about curvature. Pull one knot and the shape changes. Neither idea has been proven, and both face the same obstacle. Experiments can't yet probe the tiny scales where the differences would show up. It's like knowing two chefs use different secret techniques but being unable to taste the dish to tell which one you prefer. When physics breaks down in a collapsing universe, several familiar concepts may also break down. Causality, the idea that cause comes before effect, could become fuzzy. The notion of a single timeline may lose its meaning. Picture a crowded subway car where everyone presses forward, individual identities blur and movement rules don't apply the same way. In such a crush, you can't follow one person from platform to platform, just as you might not be able to follow the usual laws of physics through the most extreme stages of collapse. The good news is that studying this breakdown is useful beyond thought experiments about doom. Progress toward a consistent quantum gravity framework helps make sense of black holes and the very early universe, and it drives advances in mathematics and experimental techniques. Observations from telescopes and particle colliders keep tightening the room for possible theories, even if they haven't landed on the final answer yet. It's a bit like remodeling a kitchen. You don't need to lift the entire roof to know that the sink and the stove have to be connected in some sensible way. Finally, while the precise fate of a collapsing universe remains speculative, the central point stands: classical physics reaches its limits and a quantum description of gravity must take over. Until a tested theory appears, the deepest moments of collapse are terra incognita, unfamiliar land. Scientists keep mapping the edges with thought experiments, analog models, and ever more sensitive observations, so when the fog clears we won't be completely surprised. And if a convincing theory ever arrives, it will likely change how we talk about time, space, and reality itself, which sounds dramatic, but it's also the sort of surprise scientists secretly enjoy. Can information survive the collapse? Physical rules that govern tiny particles suggest information, the exact arrangement and state of everything, is not casually erased by normal processes. By information, here we mean the specific details that tell you how a system was arranged, the exact positions and speeds of particles, the particular letters printed on a page, the pattern of ripples on a pond. In quantum physics, this idea is often summarized by the notion that if you knew the complete state of a system, in principle you could run the laws backward and recover its past. That sounds neat on paper, but the universe has ways of making, in principle, very different from, in practice. A collapsing universe would pile matter and energy into unimaginably tight, hot conditions where particles bump and mix like cream stirred into coffee. When things get that thoroughly mixed, the original patterns are spread out into tremendously complicated correlations among many particles. Think of baking. Once eggs, flour, and sugar are combined and cooked, you can't point to a single lump and say, that was the sugar. The ingredients' identities are still there in atoms and chemistry, but the original recipe is effectively unrecoverable without heroic detective work. Black holes give a concrete example of why physicists worry about survival of information. A black hole swallows stuff and hides it behind an event horizon, a one-way surface, and when black holes slowly emit faint radiation, that radiation looked random at first. If the radiation carries no memory of what went in, then information seems to vanish. Many scientists now think the deep quantum rules prevent outright destruction. The missing data would be encoded in subtle correlations, like how the pattern of ashes might still reflect how a book was burned if you had infinite patience and instruments. That said, decoding those correlations would require controlling and measuring extremely tiny effects under extreme conditions, which is wildly beyond any practical ability. Unknown physics at the smallest scales complicates the story further. The collapse would push matter into regimes where gravity and quantum effects both matter intensely. Our current theories might be incomplete there. Spacetime could behave in ways we do not yet grasp. So there are two possibilities that survive careful thinking: either information is preserved in some scrambled, redistributed form, or our deepest laws permit genuine loss under conditions we do not yet understand. Both options carry big consequences for what survive means. Even if information is preserved in principle, survival in any useful sense is another matter. Retrieving scrambled correlations from a universe that has gone through a violent crunch is like trying to rebuild a shredded encyclopedia from dust motes scattered in a hurricane. Practical recoverability would be effectively zero. For life's everyday questions, like whether a particular photograph, a family recipe, or a personal memory could be recovered, the answer is bleak. They might exist as patterns in the fundamental degrees of freedom, but they would be hopelessly mixed and inaccessible. So yes, physics hints that the cosmos prefers not to destroy information outright, but no, that doesn't mean your lost keys will reappear after a cosmic bounce. Multiverse ideas, bounces and rebounds. Some cosmologists think that a collapsing universe might not be the final curtain but a setup for the next act, where the squeeze of everything eventually reverses and a new expansion begins. In these bounce ideas, the crunch is not an absolute end but a high-pressure, ultra-small state where strange rules take over, quantum effects that act like a kind of cosmic spring, pushing back instead of letting everything compress forever. Picture a toy ball squashed between your palms that suddenly pops back up. On the tiniest scales, the universe might behave a bit like that ball. At very small scales, ordinary gravity gives way to new behavior and forces that can halt collapse. Quantum pressure is one such concept. When matter and energy are packed into extreme density, the tiny scale rules of quantum physics can create resistance. Another picture comes from higher dimensional thinking, where our universe is like a sheet floating in a larger space, and a collision with another sheet can trigger a new expansion. Think of two sheets of wet paper slapping together and flinging droplets outward, messy, but effective. The technical names for these ideas vary, but the common thread is a physical process that replaces an irreversible collapse with a rebound. Observational clues could, in principle, hint at past bounces. Leftover light from the earliest hot phase of our universe, the cosmic microwave background, carries patterns and tiny ripples that cosmologists study carefully. If a previous collapse left a distinctive fingerprint, it might show up as unusual features in that background or as specific kinds of gravitational waves, ripples in space itself, that we could try to detect. It's like listening to a faint echo in a noisy room. The signal might be there, but pulling it out requires very sensitive instruments and a lot of patience. If bounces really happen, the implications are wide and sometimes surprising. One model lets each bounce produce different conditions, which leads to a kind of multiverse made of sequential rebirths, each universe a new round of the cosmic game. That raises questions about information, disorder, and memory. Does the universe reset at each bounce, or does it carry over some history? It's comparable to deciding whether to restart a video game from scratch or continue with saved progress. Some theories act like a full reset, others like a continuing storyline. Researchers treat bounce models as lively, speculative options that need more evidence. Better maps of the cosmic microwave background, more sensitive searches for primordial gravitational waves, and a deeper understanding of how quantum rules marry with gravity would all help. For now, the idea of cosmic rebound sits at the edge between bold imagination and testable science, intriguing, a little wild, and definitely not ready to be filed under settled. Scientists keep looking, like people chasing a mysterious ping on a seismograph, hoping a clear blip will tell whether the universe ends or simply bounces back for another round. Cyclic universes, eternal return or cosmic Groundhog Day? Observations show the universe is not just expanding but doing so at an ever faster clip, which makes a simple collapse back into a single crunch less likely under the physics we currently measure. The Big Crunch idea itself is easy to picture. If expansion slowed and reversed, everything would draw together until space got extremely small and hot, like winding a spring tighter and tighter. To actually get that winding to happen now, something fundamental about the stuff that speeds expansion, what physicists call dark energy, would have to change its behavior, or entirely new physics would have to appear. That's a big if. Small, quirky fact, it's like expecting a thrown boomerang to return even when someone keeps stuffing it with extra push outward. You need to change the shove first. Some scientists have proposed ways the universe could go through many such cycles, where a collapse leads to a bounce and a new expansion, repeating over and over. Think of a trampoline compressed by a heavy object until it slings it back up. In these ideas, when the universe compresses to extreme densities, rules of physics may shift and produce a rebound instead of a permanent end. These bounce scenarios are imaginative and mathematically rich, but they rely on physics we haven't confirmed yet. In everyday terms, it's like suggesting your old phone could suddenly reboot into a new model if you press the right hidden button. Neat to think about, but you'd want proof before selling the story. Exact repetition, an eternal return where every particle, planet, and life form reappears identically each cycle, runs headlong into the stubborn rule that disorder tends to increase. Entropy, the technical name for that idea, is like the rule that your room will get messy unless you actively tidy it. Each cycle would start in a very special, low disorder state to repeat perfectly, and that specialness is hard to produce naturally. Add in quantum randomness and sensitive dependence on tiny differences, the scientific version of a butterfly flapping and changing the weather, and the odds of producing the same universe twice drop dramatically. So even if cycles occurred, they would most likely be variations on a theme rather than precise reruns. No cosmic Groundhog Day, in other words. How would we know if cycles happened? Scientists look for telltale patterns in the sky, unusual signals in background radiation or repeated signatures in cosmic structures, but so far nothing forces the conclusion that our universe is one in a neat series. Current evidence favors continued expansion, which makes the cyclic take more of a speculative possibility than a supported fact. The idea remains useful, though. It pushes physicists to ask how space, time, and the laws themselves behave under extreme conditions, and it gives philosophers new ways to think about meaning and endings. And for those who like a comforting thought, the cyclic picture at least offers a dramatic final act twist, not an end, but a reset button, provided the cosmos can find it. Thermodynamics and entropy near the end. As the universe crunches inward, everything would get squeezed together and heat up. Gas clouds, stars, and the thin, tenuous stuff between galaxies would gain kinetic energy and radiation would get bluer and more intense. The basic rule that governs this behavior is the second law of thermodynamics, which says that in a closed system the amount of disorder, or entropy, tends to grow. Think of it as nature's bias toward messiness. A simple kitchen example helps. When cream is stirred into coffee, the two fluids mix and you cannot unmix them without extra effort, because mixing raises entropy. Short and sweet, that's the direction the universe's arrow of time points. Gravity acts in a weird way compared with the everyday mixing of gases, and that complicates how we count entropy. In ordinary situations, spreading things out raises entropy, but with gravity, pulling matter together into clumps, stars, galaxies, black holes, actually increases gravitational entropy. Black holes are an extreme example. They are incredibly efficient entropy collectors, and their entropy is related to the area of their event horizon rather than the volume inside. So when black holes merge during a collapse, the total entropy jumps, like combining two messy rooms into one giant disaster. It's a case where getting more concentrated equals getting more disordered. As the collapse continues, collisions between particles and extreme compression would drive the contents of the cosmos toward thermal equilibrium, meaning matter and radiation come to the same high temperature and energy is shared widely. In that state there is very little free, usable energy left to do organized work. The universe becomes a hot, homogeneous soup where the local differences that drive engines and life have been erased. Practical lives offer an analogy. A battery powers your device until the voltage is equalized and the usable charge is gone. During a crunch, the battery of the cosmos runs flat, though on a much grander scale. The accounting of entropy in this final, dense phase gets tricky because our usual thermodynamic rules meet gravitational extremes and quantum effects, and that's where current physics gets humble and says, we don't fully know. The net picture from thermodynamics is bleak for order. Entropy grows and usable gradients fade, unless some new physics changes the rules. This means that while structures can form and be spectacular on the way in, the end state favored by standard thermodynamics is a very hot, very disordered one where energy is spread thin in useful forms. A little cosmic humor, it would be like trying to organize a rock concert after everyone has left and the instruments have melted into a single unplayable heap, messy, loud in memory only, and not much left to do except accept the mess. Is time different in a collapsing universe? Inside a universe that has stopped stretching and begun to shrink, the bookkeeping of time changes mostly on paper rather than in your wristwatch. Space and time are linked in Einstein's picture, so as the universe's size, scientists call this the scale factor, goes down, the mathematical descriptions we use to mark moments evolve too. That doesn't mean clocks mysteriously pause, it means that which moments we call now, and how we compare one clock to another depends on the perspective we pick. Think of it like switching map projections. The map looks different, but the landscape hasn't vanished. Locally, time still feels normal. An astronaut falling along with a collapsing patch of the cosmos experiences her own seconds, proper time, just like anyone else, and her heartbeats and watch ticks remain reliable measures for her. On the other hand, gravity affects how time appears to others. Stronger gravity makes clocks tick more slowly compared to clocks far away. That's the same effect engineers correct for when they make GPS work. Satellites' clocks have to be adjusted because gravity and motion tweak the rate of time. In a big crunch, as matter piles up and gravity gets intense, such differences grow. But if the whole universe is collapsing and there's no outside vantage point, there's no far away clock to compare to, which makes statements like, time slows down for the universe, a bit empty without extra context. Because the direction of time in daily life is tied to entropy, the way disorder tends to increase, the arrow of time probably keeps pointing the same way even while the universe contracts. Mixing syrup into tea doesn't unmix itself just because the room gets smaller, and a messy desk won't spontaneously tidy up when walls press inward. Most physicists expect that entropy will continue to rise through a collapse, so cause and effect relationships remain intact and memories still point backward toward lower entropy states. Some speculative ideas in quantum cosmology suggest more exotic possibilities, like a bounce that replaces the crunch, but those are conjectures that try to reconcile gravity with quantum rules rather than established facts. Near the ultimate end of collapse, classical descriptions break down and weird effects kick in. General relativity predicts that curvature and density can become extreme, and our usual notion of time tied to smooth clocks and continuous change may fail. In practice, that means physical clocks would stop working long before any mathematical time reaches zero, atoms fall apart, radiation floods everything, and normal processes that define seconds vanish. So while equations can extend time coordinates arbitrarily, physical time, the kind that governs chemistry, biology, and coffee cooling, may simply cease to be meaningful in the final, extreme stages. No cosmic timeout to finish your taxes, in other words. In short, different is a matter of viewpoint. Clocks carried by people or probes keep measuring proper time normally for them. Gravitational strength can make comparisons between distant clocks tricky, and the thermodynamic arrow of time most likely still points forward during collapse. Deep down near a singular crunch, however, the whole concept of time may be reshaped by physics we don't yet have nailed down, and that's where the line between careful science and science fiction gets delightfully blurry. Observable signs we might be heading toward a crunch. Current measurements show that the universe is getting bigger faster right now, so a change toward collapse would have to show up as a steady slowdown and then reversal of that growth. One clear sign would be a shift in how light from distant galaxies is stretched. If galaxies that have been moving away begin to slow or head back toward us, the red tint in their light would lessen and could eventually turn toward blue. Astronomers watch this by comparing precise spectra from the same galaxies over many years. It's like checking if a distant car on the highway is slowing by listening to the pitch of its engine. Supernovae that have served as standard candles, stars with predictable brightness used to judge distance, would start to appear brighter than the expanding universe predictions, because distances would stop growing as fast or begin shrinking. The faint afterglow of the early universe, the cosmic microwave background, would also tell a story if contraction began. That glow behaves like the heat left in a room after a heater was turned on long ago. As space compresses, it would warm up a bit and shift toward higher energies. Detecting that would require very precise measurements, since changes would creep in slowly. A useful everyday analogy is pumping air into a bicycle tire. The air feels warmer as it gets compressed, even though the change isn't dramatic at first. Local dynamics would show practical and visible effects. Galaxy clusters that are barely holding together might start to pull inward more strongly, and collisions between galaxies would become more frequent. In our neighborhood, the Milky Way and Andromeda are already on a collision course due to local gravity, but a global shift toward contraction would make interactions like that happen more often and on larger scales. Observers would note a rise in the speed of mergers, more gas funneled into black holes, and a general increase in energetic events. Quasars and bright cores could flicker more as they're fed. It's a bit like seeing more cars pile into a traffic jam when everyone starts heading to the same exit. Some of the most subtle signatures are the ones astronomers pay closest attention to because they distinguish slow trends from local noise. Tiny changes in the measured recession speed of very distant objects, tracked over decades, would be a smoking gun. These changes are minuscule, comparable to measuring the growth of a fingernail over many years, so only the most stable, long-term instruments can spot them. In addition, maps of galaxy positions made over time would show the large-scale web of matter becoming denser, voids would shrink and filaments would thicken. Scientists cross-check all these signals, light shifts, background warming, increased collisions, because any one effect could be caused by something else, like local gravitational quirks or instrument drift. Think of it as combining weather reports from satellites, radars, and ground stations before deciding a storm is really coming. Practically speaking, all of these signs would unfold extremely slowly on human timescales, and detecting them needs patience and precision. Telescopes and space observatories keep monitoring supernovae, spectra, and the cosmic glow, stacking data year after year to tease out the faint trends. So while the picture of a universe collapsing back in on itself makes for dramatic headlines, the real work is quiet and meticulous, measuring whispers in light, watching galactic dances, and waiting to see whether the cosmos keeps stretching or starts to sigh and pull back. A little cosmic humor helps. Scientists are essentially keeping a very long-term receipt for the universe's expansion and checking it every so often. Simulations and computer models of collapse. Computer models let scientists play out different cosmic endings by changing a handful of inputs and watching what happens next. They take a snapshot of the universe's lumpiness, how matter is clumped in space, and then let gravity and whatever else you tell the model to include do the rest. In practice that means starting from measurements of tiny ripples seen across the sky and evolving them forward, like running a weather forecast but for everything in the cosmos. One common approach follows many particles that represent bits of matter and tracks how they pull on one another. These n-body simulations are basically a very elaborate ant farm. Each ant feels the pull of many others and the whole colony shifts in response. Software used by researchers implements this idea, and runs on powerful computers so that the collective motion of huge numbers of particles can be calculated without waiting centuries. Simpler gravity rules often work well on large scales, but if a collapse gets severe enough, the full rules of Einstein's gravity, more complicated math, must be used, and that requires much more computing power. Models do more than just gravity. Gas, pressure, cooling, and sometimes the messy physics of star formation are added to make the outcome more realistic. A hydrodynamic code treats gas like weather in a pot: it flows, it heats, it cools, and it collapses under its own weight in places. Putting these pieces together lets researchers compare possible collapse scenarios. In some runs the whole cosmic brew keeps drifting apart, while in other runs it slows, stalls, and reverses into contraction. Small changes to how a repulsive force called dark energy behaves are often the deciding factor. If this repulsive force stays as strong as we observe today, most simulations show runaway expansion rather than a crunch. Turn that force down or make it act attractive, and the balance tips toward a possible collapse. Running a collapse scenario is computationally demanding and full of practical choices. Resolution matters. A model that treats galaxies as single points will miss internal chaos, while a model that resolves stars costs a fortune in computing time. Researchers therefore use a mix of large-scale runs to see the big picture and zoomed-in simulations to study details, the way a filmmaker switches between wide shots and close-ups. Another challenge is uncertainty. We don't yet know exactly how dark energy behaves, so scientists run families of simulations, each one with slightly different rules, to map out which cosmic fates are possible and which are not. Simulations also predict observable signs that would point toward collapse, so they are not just theoretical toys. For instance, a universe heading for a crunch would show growing inward motions on the largest scales and increasing clumping of matter. Astronomers can look for such trends in galaxy surveys and maps of background radiation. In short, models act like virtual laboratories where hypotheses about dark energy, gravity, and matter can be tested and where the telltale fingerprints of a possible collapse are identified. They don't give absolute answers yet, but they help narrow down which cosmic recipes lead to a crunch and which leave the universe expanding. No blender required, and thankfully no cosmic baking disasters so far. Laboratory analogs, tabletop universes. Researchers can build small systems in the lab that behave a bit like miniature universes, using waves and fluids instead of planets and galaxies. Bose-Einstein condensates, which are clouds of atoms cooled until they act like a single wave, can be nudged so that the wave patterns inside them change over time, similar to how space itself might shrink. Water tanks with carefully shaped flows, optical fibers whose light speed is altered, and specially designed materials that steer waves can all play the role of a spacetime stage. Think of it as directing a play where the stage itself bends and squeezes, and the actors are ripples, sound pulses, or beams of light. One way to mimic a collapsing cosmos is simply to change the conditions that set the size of the space in the experiment. In a trapped cloud of ultra-cold atoms, tightening the trap makes the cloud contract and the wavelengths of excitations shorten. In an optical experiment, suddenly changing the refractive index is like shrinking the distance light travels in a fixed time. In flowing fluids, speeding up a downstream flow can sweep waves inward, creating regions that behave like horizons. The outcomes of interest are changes in how waves are created, amplified, or mixed. The lab analogs let scientists watch particle-like excitations pop in and out, or hear how sound modes get scrambled when the background squeezes them. A useful everyday picture is stirring a puddle. Change the shape of the cup fast enough and the ripples look different. In a tabletop universe, changing the background fast enough can make new ripples appear out of nothing. Experiments have already seen horizon-like behavior and related emissions in several platforms, though these are analogs of principles rather than recreation of full cosmic events. For instance, flows in water tanks have produced wave patterns that mimic what happens near horizons, and cold atom setups have shown mode conversion that mirrors particle production predicted in shrinking or expanding spaces. These results help test the math that describes how fields behave when the stage itself changes. But there are big limits. A lab can mimic the behavior of waves living on a changing background, yet it cannot recreate the full gravitational field or the extreme densities of a true cosmological crunch. You won't create an actual singularity on a lab bench. Think of it as testing how actors respond to a collapsing set rather than recreating the collapsing theater. On the practical side, these tabletop universes are useful because they let physicists try out ideas that are otherwise unreachable, check calculations, explore how information carried by waves gets redistributed during a collapse, and test whether certain kinds of particle production are robust against noise. Still, noise and losses in real materials, boundaries of the device, and the fact that the analog, spacetime, is engineered rather than self-gravitating mean conclusions must be drawn carefully. Future work aims to tighten control over parameters, reduce unwanted dissipation, and use quantum simulators to probe more subtle quantum effects during contraction. It may never crush coffee cups, but it will keep theorists humble and experimentalists entertained. Philosophical implications of a finite universe. Some scientific models allow the universe's outward growth to slow, stop, and reverse so that gravity pulls galaxies, stars, and eventually atoms back together into a single, very dense state. In plain terms, that is what a big crunch means. Expansion gives way to contraction, and the cosmos becomes smaller and hotter as everything squeezes inward. If the universe is finite in time and space in that way, the simple fact of limits changes how people frame meaning, purpose, and responsibility. Everyday life gives an easy comparison. You care differently for a plant you know will live only a week than for one that might survive for years. Scarcity makes attention sharper. A finite cosmos raises clear questions about duty to future people. If the end is certain and unavoidable, should we prioritize urgent, short-term comforts or invest in long projects that benefit distant descendants? Think of saving money for a child's education versus spending it on a last-minute holiday. Both choices look different when a deadline looms. On a larger scale, debates about preservation of knowledge, art, and culture take on new weight. What should we try to pass on if there will be a final cutoff? Practical life offers models. People still plant trees whose shade they may never sit under, and that same impulse can survive even under a finite universe view. Humor helps. Even if the universe has an expiration date, most of us still file our taxes. A finite universe also pushes philosophical conversations about freedom and fate. A closed, temporally bounded cosmos can seem like a book with a fixed ending, which tempts people toward fatalism, the idea that choices don't matter because the end is written. Counterarguments are simple and human. Actors in a script still find room to play, and choices change how the story feels. Small examples: two neighbors both know their town will one day vanish in a flood, one spends the last years building friendships, the other hoards supplies. The ethical difference remains real. In other words, knowledge of an end doesn't erase agency, it reshapes priorities and colors the meaning of our actions. Religious and existential responses will vary. Some traditions may reinterpret an ending as a return or renewal, while others might emphasize moral urgency or divine judgment. People often take comfort in ritual and community. Funerals are solemn but also about memory and celebration. Finite cosmic time can intensify appreciation for beauty and relationship. Artists already know this, limited edition prints feel more precious. The same principle applies to sunsets and songs. A touch of humor helps. Knowing the cosmos might collapse does not mean you should skip dinner. Enjoying dinner is exactly the point for many. Finally, thinking about a finite universe teaches scientific humility and practical focus. Cosmology contains real uncertainties, and policy decisions should be based on known risks that affect generations now rather than speculative cosmic endpoints. Still, the idea of finitude can inspire cultural shifts. It can motivate efforts to preserve knowledge, to make science and art that outlast individuals, or to foster a global ethic of care. Consider two builders: one makes a temporary shelter, the other carves a stone bench meant to be seen by many. Both choices matter. The deep lesson is comforting in its own way. Limits can sharpen value, push us toward kindness, and give urgency to what we do today, without turning life into a panic room. Life and civilizations facing a contracting cosmos. A contracting universe would slowly squeeze the space between galaxies and shorten the wavelengths of background light, turning the faint microwave glow into progressively hotter, more energetic radiation. As that background energy rises, it acts like a cosmic heat lamp turned up notch by notch. This wouldn't be a sudden zap, rather a long tightening that pushes temperatures up and makes distant parts of the sky close in, so what once looked like a vast empty night becomes a crowded, brighter one. Local systems would feel the squeeze first. Gravity would pull galaxy neighbors closer and collisions between large structures would become more common, changing the pattern of star formation and stirring up gas. Planets that once had stable orbits might see those orbits shift under new gravitational nudges. Life on a planet warmed by its star could be pushed into refuges, underground caverns, deep ocean vents, or shaded polar regions. Microbes that today thrive in boiling hot springs show how life can cling on in extreme heat. They might be the last biological holdouts when surface conditions deteriorate. Civilizations would confront practical, familiar problems amplified to cosmic scale. Energy management would become central. Rising background heat reduces the temperature difference that machines rely on to generate useful work, making power production harder. Picture trying to run a refrigerator when the kitchen slowly becomes tropical. That's the challenge, but for everything from factories to data centers. Redundancy and decentralization would help. Just as humans today store seeds in vaults and keep off-site backups of data, future societies might build multiple, widely separated archives and habitats, some underground, some deep under ice, others in strong orbit around dense, stable objects. Simple examples from current life: bunkers for wartime shelters, Antarctic research stations designed for isolation, and submarine crews trained for long, dark stretches, offer a model for how to organize people and resources when the external environment becomes hostile. Engineering responses would mix low-tech resilience with high-tech gambits. Thick insulation, radiation shielding, and controlled habitats are straightforward adaptations. On the bolder side, societies might try to relocate to regions where gravity keeps matter more tightly bound, galaxy cores or massive clusters, because those regions would remain coherent longer during the contraction. That's a risky move though, since such regions are dense and active and could be hazardous in other ways. Think of moving into a busy city to avoid rural flooding. You escape one danger and step into another. Communication and coordination become harder as cosmic distances shrink and sky brightness interferes with long-range signals. Civilizations would likely prioritize local networks and build protocols to pass knowledge quickly and redundantly. For instance, instead of relying on a single planetary archive, multiple copies could be sent in different directions, buried, launched, or integrated into hardy organisms. Nature's strategy of spreading offspring widely, seeds scattered by wind, animals migrating, offers an apt analogy. Humor helps here. It's like sending postcards to every mailbox in the neighborhood because you don't trust the postal service anymore. Long-term thinking shifts from expansion to preservation. Scientific and cultural records could be compressed into durable formats and stored in low-entropy places where heat and radiation do as little damage as possible. Examples today include using quartz glass or synthetic crystals for long-lived data storage, and banking seeds in cold, stable facilities. Yet, as the background energy rises, cold storage loses effectiveness. Clever engineering must find ways to maintain low-temperature pockets. That's a tall order, akin to trying to keep ice cream from melting in a steadily warming house, and would demand constant energy and adaptive systems. Advanced civilizations might explore extracting useful work from the changing cosmos rather than only hiding from it. Accreting material into compact objects releases energy. Using such processes could temporarily power habitats under stress. However, these options are speculative and technically demanding, and they come with their own hazards like intense radiation. Even so, the underlying strategy is pragmatic: turn problems into resources when you can, but don't bet everything on one solution. Redundancy, adaptability, and a cultural commitment to preserving knowledge would increase the odds that something of a civilization survives the contraction's harsher phases. Psychological and social effects should not be underestimated. People adapt culturally to long-term threats by changing values, rituals, and expectations, just as communities today adapt to chronic environmental stress. Maintaining morale, passing down practical skills, and keeping flexible governance will be crucial when infrastructure must be constantly repaired or relocated. A bit of humor, stories, and art could become survival tools in their own right. Comfort is a strategy too. In the end, facing a contracting cosmos would be a contest between the laws of physics and the ingenuity of life. Some strategies are straightforward extensions of things we already do: diversify habitats, protect archives, and build resilient systems. Others demand leaps in engineering and cooperation. Nature shows both stubborn persistence and creative adaptation. Human culture adds planning, technology, and an ability to coordinate on scales unlike any other species. That combination, practical preparedness plus inventive thinking, would be the best bet for any civilization trying to keep its lights on as the universe tightens its grip. Technology to escape or delay the crunch. A shrinking universe would squeeze space itself, bringing galaxies closer, heating gas, and piling up radiation as distances get smaller. Astronomers already track how fast the cosmos is stretching by watching supernovae, mapping galaxies, and measuring tiny shifts in light. Those same tools would give an early warning if expansion slowed and reversed. Telescopes and sky surveys are our thermometer and speedometer for cosmic motion, and better measurements of the mysterious, dark energy that drives expansion are essential if humans ever hope to plan a response. In plain terms, we need to know the problem before trying to fix it, just like checking the weather before deciding to sail. Detecting a trend early is one thing, changing the universe's behavior is another. The idea of altering dark energy or the vacuum of space is theoretical and would demand conditions and energies far beyond what today's technology can produce. Think steering an ocean with a teacup. Still, theoretical proposals exist in physics that talk about creating regions of different vacuum energy or nudging the field that controls expansion. Those remain speculative, and nobody has a working blueprint. This is not a call to give up, though. It is a clear message that practical strategies will likely focus on buying time and preserving knowledge rather than flipping a cosmic switch. On the more practical side, technologies we can develop now and in the near future could extend civilization's survival window. Building large, self-contained space habitats is a good example. Concepts like rotating cylinders or toruses produce artificial gravity by spin, picture a playground roundabout scaled up to town size, and could house agriculture, life support, and industry. The International Space Station already recycles water and air and grows small plant experiments. Expanding those systems into closed-loop ecology that works for decades would be a direct, useful step. Mining asteroids for metals and volatiles would provide the raw material to build and expand those habitats, and solar sails or advanced electric and fusion-driven propulsion under research could let us move heavy structures around the solar system or to farther resources. Not glamorous, but practical. Learn to grow your food indoors, and you survive storms better. Another practical thread is information and redundancy. If physical escape becomes impossible, preserving human knowledge, culture, and DNA could be a fallback. Deep, durable archives, encoded in multiple ways, stored in diverse locations like the moon, asteroids, and in crystalline media, would act as a cosmic time capsule. Think of it as backing up civilization to multiple hard drives placed in different rooms. Redundancy matters. Running simulations and building robust artificial intelligences to continue research and possibly find solutions is also sensible. These AIs would need power sources designed for long timescales, nuclear reactors with careful shielding, or systems that tap into local energy reservoirs such as small fusion plants once mastered. Some moonshot ideas aimed at true escape are often discussed in scientific circles, though they remain far from practical. Creating a baby universe or tunneling to another region of spacetime comes from deep theoretical physics, and would require manipulating exotic states of space, concepts that are math-heavy and experimentally untested. Wormholes are another popular idea. They appear in equations as shortcuts between distant regions of space, but keeping one open would need forms of matter and energy we haven't observed. All of these sound like science fiction because, at present, they are. Still, exploring the math and running tabletop analogs in laboratories helps physicists learn which paths are dead ends and which might someday yield surprises. Finally, incremental resilience is both realistic and empowering. Improving global energy systems, mastering long-duration life support, perfecting in-space manufacturing, and training a scientific culture that shares knowledge widely will not guarantee survival of the universe, but they make it more likely that intelligent life can last longer and adapt. It's like putting better locks, storm shutters, and an emergency pantry in a house on a floodplain. You may not stop the flood, but you can survive longer and help rebuild. And while we cannot yet pull the cosmic emergency brake, investing in measurement, sustainable habitats, resource access, and information preservation is the least fanciful and most practical route humanity has for buying time, and maybe, someday, finding a real escape hatch. Cultural and artistic visions of a cosmic collapse. Artists, writers, and performers often turn the idea of the universe folding in on itself into images people can feel. The Big Crunch, simply put, is the idea that the universe might stop spreading out and begin to shrink back, like a balloon that lets the air out, and creators use that image to talk about endings and new beginnings. That simple metaphor helps translate a huge cosmic idea into everyday experience. Think of family photos being taken from walls and stacked into one small box, or a parade that slowly closes its route until everyone meets in the center. Painters and visual artists translate collapse into compressed space, heavy colors, and crowded composition. A canvas might show buildings leaning inward, or a horizon crushed into a single thin band. Installation artists will literally reduce the gallery footprint, building rooms that make visitors stoop and squeeze, which creates a physical sense of pressure. Light artists play with intensity and shadow, dialing down brightness until the space feels swallowed, a technique used to make viewers sense the pull of something closing in. These choices are easy to relate to. Standing in a too small elevator gives the same immediate feeling as a painting that seems to close around you. Writers and poets favor collapse as a metaphor for loss and return. Short sentences can mimic the final beats of things. Long, winding sentences can mirror the slow contraction of a story world. A poet might use the image of a tide that goes out and never comes back to describe memory fading, while a novelist might have entire cities drawn inward, people clustering in tighter communities. Everyday examples, like clearing an overfull closet or collapsing a folding table after a party, give authors handy images for describing how space and time can contract emotionally as well as physically. Composers and sound artists create auditory versions of a cosmic shrink. Low, sustained tones and a dropping pitch can make listeners feel weight increasing, like gravity getting stronger. Percussion that slows and thickens, or a choir that moves from many voices to a single humming note, mirrors the idea of things coming back together. You know that unsettling moment when a song fades into a single repeating note? That's the same effect, condensed into a few bars. Musicians sometimes use these tricks to evoke the hush of everything being drawn inward, and it works because sound hits the body directly. Performance and fashion borrow the same themes but with movement and garment. Choreographers will stage dances where the stage itself seems to compress, with dancers moving from wide, expansive patterns into tight, interlocking formations. Costumes can become more body-conscious or layered so the silhouette narrows and weight seems to press inward. Even in everyday life, people fold sweaters and pack suitcases, turning bulk into neat bundles, a mundane act that artists elevate into a ritual of fitting a world back into itself. There's often a wink of humor in this art. A designer will show an end-of-universe trench coat with so many pockets it collapses into a pouch, practical and theatrical at once. Across cultures, the collapse motif gets used to ask big human questions about closure, memory, and rebirth. Rituals where communities gather to reduce offerings, clean a temple, or consolidate belongings echo the same pattern on a human scale. That shared act of bringing scattered pieces together feels like a small, social big crunch. Humor helps too. Comedians turn cosmic collapse into jokes about cleaning out the fridge or the panic of losing Wi-Fi when everything has to come back to one source. The point artists make is practical, whether through paint, sound, movement, or clothes. The image of a universe pulling inward helps people process endings and imagine what might come after. How different physics would reshape chemistry and biology. As the cosmos turns from expansion to collapse, the first and most reliable change is that everything gets hotter and denser. That means atoms start feeling a lot more energetic collisions and stronger squeezes, and chemical bonds that once made water, proteins, and rock stable begin to break apart. A simple way to think about it: heat is like an excited toddler who won't stop pulling blocks apart. When the toddler's energy keeps rising, the towers, molecules, fall. Ordinary chemistry depends on electrons hanging around nuclei in stable ways. When those electrons get stripped away by intense light or forced into nuclei by crushing pressure, the familiar behavior of atoms vanishes. Higher radiation levels and tightened packing change which reactions can happen at all. Low-energy chemical reactions, like rust forming on iron or sugars fermenting in a jar, rely on modest temperatures and slow molecular encounters. In a collapsing universe, photons grow more energetic, like sunlight turned up to a dangerous, blue-shifted glare, and they kick electrons free in a flash. That ionization destroys delicate molecules faster than new ones can form. A household example: leave an egg in a hot pan and the proteins unravel and coagulate. Crank the heat so high that the egg flames and the proteins fragment, and you no longer have a cooked egg, just a chemical mess. Chemistry under collapse becomes that messy very quickly and permanently. Pressure adds another layer of mischief. Squeezing materials changes how electrons arrange themselves around nuclei, and those arrangements are what give elements their chemistry. Under high pressure, elements that normally behave one way can act very differently. Carbon that forms flexible graphite here might behave more like diamond under extreme squeeze, and hydrogen can become metallic and conduct electricity. These are not just academic curiosities, they show that basic chemical rules shift when environments change. Eventually, if pressure becomes extreme enough, electrons can be forced into protons, making neutrons. In that regime, the concept of chemistry itself collapses because chemistry needs electrons to make bonds. Think of it as removing the Velcro strips that let molecules stick together. Biology depends on the stable, slow chemistry of molecules like DNA, proteins, lipids, and water. Life's machines run on tiny batteries and carefully folded shapes. ATP is a chemical battery, protein folds are precise sculptures, and membranes are thin oily walls that keep the cell organized. Heat and ionizing radiation are ruthless to these features. Proteins unfold and stop working, cell membranes become leaky, and DNA strands break. A familiar life example: leave meat in the sun too long and bacteria and heat spoil it. Now replace the sun with a universe that steadily intensifies its glare, and all biological repair systems are overwhelmed. Even extremophiles, microbes that thrive in heat, pressure, or radiation, rely on particular energy gradients and chemical cycles. Those niche habitats might hold out longer, like deep-sea vent communities clinging to geothermal heat, but the broader loss of stable chemistry slowly erases the energy flows life needs. Dynamic gravitational changes make survival on larger scales unlikely as well. As space shrinks, orbits drift, tidal forces grow, and planets can be heated from within or torn apart. That rearrangement destroys the steady environments that ecosystems require. Consider how tides from the moon gently tug Earth's oceans now. Scale that up and the tidal stress becomes a cosmic blender. Biological communities that once adapted to seasonal cycles and quiet nights are suddenly subjected to wildly changing light, temperature, and mechanical stress. Evolution is slow and needs some continuity. Collapsing physics delivers only relentless, chaotic change. There is a final, humbling limit. At extreme densities and temperatures, the laws we use to describe chemistry and biology break down. Known physics tells us that at such extremes, matter behaves in ways we cannot reliably predict with current theories. In plain language, chemistry and biology as we know them lose meaning. The familiar alphabet of atoms and bonds fades into something governed by unfamiliar rules. That's not science fiction bravado, it's an honest admission that beyond a certain threshold our descriptions no longer map onto reality. For everyday life, this means molecular machines stop working long before that mysterious frontier is reached. So in a collapsing universe, chemistry would shift from rich and varied to harsh and destructive. Familiar molecules would be ionized or crushed into new, often less useful forms, and novel, short-lived species might appear only to be zapped apart. Biology would first see ecosystems collapse as habitats, energy sources, and molecular integrity vanish, and then life itself would become impossible once the very basis of chemistry disappears. It's a grim chain of events, but at least you won't have to suffer the indignity of frozen dinners. The universe will have taken care of the heat. Could the Big Crunch seed a new Big Bang? Astronomers watching distant galaxies find that the universe is not slowing down but speeding up in its expansion, which makes a full collapse into a dense ball much less likely given what we know today. If gravity were somehow to win and the expansion reversed, matter and radiation would be squeezed into a much smaller volume, raising temperature and pressure to levels we can only talk about in simple metaphors. Think of it as stuffing an overfull suitcase. Everything gets closer together, hotter, and more chaotic. Not impossible in theory, but very different from what our best measurements are telling us right now. Some theoretical ideas say that when space gets extremely squeezed, the rules of ordinary physics break down and new quantum behavior kicks in, which could stop a true singularity, that point of infinite density, from ever forming. In simpler words, the universe might bounce rather than smash into an infinitely tiny dot. One way to picture this is a rubber ball hitting the floor. It compresses and then springs back, though the microscopic reason is very different. Certain research approaches describe mathematics where space itself resists being crushed and rebounds, opening a door for a new expanding phase. Other speculative notions compare a collapsing region to a black hole creating a little separate universe on the inside. These ideas are intriguing but far from proven. A major puzzle is entropy, the measure of disorder. Natural processes tend to make things more disordered over time, and a new big, clean start like our own early universe would need a very low level of disorder. Crushing everything together usually doesn't lower disorder. Picture shoving a messy pile of clothes into a suitcase. They are still messy when you unzip it again. For a collapse to seed a fresh, low-entropy beginning, some mechanism would have to reset or hide that disorder, or the physics of the bounce would have to filter and reorganize information in a clever way. Scientists have proposed ways this might happen, but these involve physics we haven't tested yet. Observationally, the growing push of accelerated expansion makes the collapse-then-bounce scenario a remote possibility with current evidence. Still, our understanding of the ingredients driving expansion, the mysterious dark energy, is incomplete, and quantum gravity remains an open frontier, so the door isn't shut. If future experiments change our view of dark energy, or if a workable quantum theory of gravity predicts bounces that match observations, that would revive the idea in a big way. For now, it's a fascinating thought experiment, a cosmic reset button that may or may not exist, and one that keeps theoretical physicists both hopeful and sleep-deprived in equal measure. Tests and observations to discriminate fates. Astronomers test whether the universe will keep expanding or turn around by measuring how fast it expands now and how that speed changes over time. One basic tool is the measurement of galaxy redshifts. The further away a galaxy is, the more its light is stretched to redder colors, and that gives a snapshot of expansion at different distances. Supernovae of a certain type act like light bulbs of known brightness. When one goes off in a distant galaxy, we can compare how bright it appears to how bright it should be, and that tells us how far away the galaxy is. Using many of these standard candles lets scientists trace whether expansion is slowing or speeding up. It's like checking whether the speedometer needle on the cosmos is drifting up or down. The cosmic microwave background, or CMB, is another key piece of evidence. This faint glow is the leftover light from when the universe was very young, and its pattern of tiny hot and cold spots carries information about the universe's overall shape and content. Think of it as the wallpaper of the cosmos. The pattern tells you whether the room is curved like a sphere, flat like a sheet, or saddle-shaped. If the universe is strongly closed, curved like a sphere, gravity has an easier time pulling things back together, which would favor a collapse. Measurements of these patterns, combined with studies of galaxy clustering and ripples known as baryon acoustic oscillations, BAO, act like a set of rulers and protractors to measure geometry and distances. Gravity's role is tested by watching how structures grow. Galaxies and clusters form by gravity pulling matter together, and the rate at which small clumps grow into big clumps depends on how much matter there is and whether some repulsive force, dark energy, is pushing things apart. Astronomers count clusters and map how galaxies group at different times. If gravity were to eventually win, we would expect a history where structure growth accelerates in a certain way. In contrast, a strong repulsive effect would slow down that growth, like trying to build a sandcastle on a beach with rising tides. Gravitational lensing, where massive objects bend light like a thick glass, helps too, because it reveals where mass actually sits, even the invisible dark kind. There are also very patient clocks involved. The so-called redshift drift test watches the tiny change in a galaxy's redshift over many years. It is a subtle effect, but its sign tells you whether the expansion is speeding up or decelerating. Imagine watching cars on a long highway and noting whether their spacing very slowly increases or decreases. You'd need a long time and a keen eye, but the conclusion would be decisive. Combining redshift drift with supernovae, BAO, CMB, and lensing data is like interviewing multiple witnesses who each saw a different angle of the same event. Together they reveal the full story more reliably than any single witness. Dark energy's behavior is summarized by a single number often called W, which compares its pressure to its energy density. If W is less than -1/3, the universe accelerates, and that makes a big crunch unlikely. If instead the effective pressure were positive enough or the overall matter density were high and curvature positive, then deceleration and eventual collapse become possible. Scientists try to measure W and whether it changes with time by combining all of the tests above. It's a bit like checking a thermostat, a pressure gauge, and a fuel meter all at once to decide whether a long road trip will end at a sunny beach or back at the mechanic's garage. Local checks also matter. The motions of nearby galaxies, the total amount of matter implied by lensing compared to what we see as stars, and the ages of the oldest stars provide consistency tests. If the universe were heading for collapse, we might also see hints in early structure formation or odd behavior in cosmic expansion history that can't be fit by a smooth, ever-accelerating model. Scientists are careful, they want multiple, independent lines of evidence that agree. That way, conclusions aren't based on a single quirky observation, like deciding to move house after one storm. Finally, future instruments and long-running surveys sharpen all these tests by measuring fainter objects and tiny changes. More precise maps of the CMB, deeper galaxy catalogs, better supernova samples, and direct redshift drift measurements will narrow the possibilities. In short, astronomers act as cosmic detectives, collecting lights, ripples, and bends in space, to tell whether the universe will expand forever, slow and stop, or turn around and crunch. The tools are simple in idea, but the measurements require patience and fancy equipment, and yes, sometimes it feels like trying to weigh an elephant with a kitchen scale, while the elephant waits politely. Why current data favors expansion, for now. Light from faraway galaxies carries a simple message: most of them are moving away from us. Astronomers measure how fast those galaxies recede and how bright certain exploding stars appear, and those measurements together tell a consistent story: space is stretching and the stretching is speeding up. Exploding stars called Type Ia supernovae act like reliable light bulbs. If a known bright bulb looks dim, it must be far away. That dimness pattern was one of the first clear signs that the expansion isn't slowing down. Other clues come from the faint afterglow of the early hot universe, a smooth microwave glow peppered with tiny spots that act like cosmic fingerprints. Those spots reveal how much stuff there is and the overall geometry of space, in simple terms whether the universe is curved like a ball, flat like a table, or saddle-shaped. The maps of how galaxies are arranged also show a preferred spacing, like ripples frozen in place, and those ripples match the same expanding, accelerating picture. The invisible push that makes the expansion speed up gets called dark energy, a name for whatever is acting like a gentle, constant pressure that fills space. Think of it as an invisible syrup that doesn't run out as the kitchen table expands, its effect stays roughly the same even when a lot more room opens up. If you imagine raisins in a rising loaf of bread, the raisins move apart because the dough grows. Dark energy is more like the dough's recipe that keeps inflating the loaf rather than raisins pulling each other apart. Because data suggests this invisible influence behaves almost like a constant everywhere, it keeps driving expansion instead of letting gravity pull everything back together into a big crunch. Measurements line up in a reassuring way. The microwave afterglow tells us the universe's large-scale shape and how much of the contents are the normal kind of matter, the weird invisible matter, and the dark energy-like component. Those pieces put together point to a universe that is not dense enough in ordinary stuff and dark matter to halt expansion. Local gravity still rules close-up, galaxies and clusters stay bound, like marbles glued together on an inflating balloon, but on cosmic scales the push wins. There is a small tension, though: different ways of measuring the current expansion rate give slightly different answers. It's like using two trusted thermometers that disagree by a hair. It could be the instruments, or it might be a clue that something new is hiding in the data. Either way, the disagreement is not big enough yet to overturn the overall conclusion. To get a true big crunch, something dramatic would have to change. Either there would have to be far more attractive gravity than we can account for, or dark energy would need to turn from a gentle push into a pull. Current observations give no sign of that flip. So for now the universe looks like it's on a long stretch away from collapse, more akin to a slow road trip with the accelerator pressed gently down than a car making a U-turn. Scientists keep watching and measuring, because new instruments might reveal surprises, but at the moment the best and most consistent data favor continued expansion rather than a return ticket. Looking ahead, the future of cosmology research. Precise measurement of how fast the universe is expanding will remain central, because that expansion rate is the main clue about whether a big collapse is even possible. Astronomers use things called standard candles, objects whose true brightness we can estimate, to judge distances, and they watch how galaxies move away from us, much like tracking cars on a highway to see if traffic is speeding up or slowing down. New sky surveys and space telescopes will collect far more of these distance markers, and that larger, cleaner dataset will help rule out some collapse scenarios while making others more plausible. Think of it like upgrading from a cheap speed gun to a network of traffic cameras. The picture gets a lot clearer, even if the traffic is still messy. Listening to the universe in different ways will also grow more important. Gravitational waves are ripples in space produced by huge collisions. Detectors on Earth can pick them up and give a completely different kind of information than light does, like hearing thunder instead of just seeing lightning. Neutrino observatories, sensors that catch ghost-like particles that zip through matter, provide yet another angle, probing the most extreme events. Combining these senses is called multi-messenger astronomy, and it's like using sight, hearing, and smell to solve a mystery. More senses mean fewer blind alleys. This approach helps test whether our basic ideas about space, time, and gravity hold up under extreme conditions relevant to a potential collapse. Computers will run ever more realistic simulations of whole universe scenarios, from steady expansion to a dramatic contraction, helping researchers understand the domino effects of one small change in physics. These simulations require clever algorithms and massive computing power, and machine learning will be used to spot patterns that humans might miss, much like how navigation apps learn traffic patterns from millions of drivers. Theoretical work will try to link the big-picture behavior of the cosmos to the tiny-scale rules of quantum physics, which is really asking how the rules for very small things might change the fate of everything. Simple explanations will be sought for complex math, because if predictions are going to guide observations, they have to be testable. Collaboration across fields and between countries will shape the future, with astronomers, particle physicists, computer scientists, and even philosophers and educators joining forces. Citizen science projects can let the public help classify galaxies or search for unusual signals, which is both practical and inspiring. Volunteers have already helped discover rare phenomena by eyeballing images faster than computers. Practical benefits will spill over into everyday life too. Improvements in detectors, image processing, and data handling often find uses in medicine, communications, and navigation. In the end, humility and patience will be part of the toolkit. The universe doesn't hand over answers quickly, but step by step, better instruments and smarter ideas will sharpen our sense of whether collapse is a real future or just a dramatic thought experiment. In short, the big crunch is the simple what-if where the universe stops expanding and starts shrinking, pulling galaxies and everything inside them back together. If it happened, things would get hotter and tighter until familiar structures, stars, planets, maybe even atoms, couldn't hold their shape anymore. Think of it like a stretched rubber band snapping back, or a crowded elevator getting so full nobody has personal space left. Right now, the best hints we have suggest the universe is still stretching out, so a crunch is only one possibility, not a done deal. Thanks for sticking with me through this cosmic thought experiment. Your curiosity is the real engine that keeps these questions alive. If you enjoyed the ride, like the video and subscribe so you don't miss future episodes where we'll tackle other big ideas in plain language. Next up, why the universe might keep expanding forever and what unseen stuff could be behind it. Drop a comment with which doomsday or wonder you want to explore next, heat death, black holes, or something stranger, and share this with a friend who loves spacey what-ifs. See you in the next video. No need to panic about hypothetical collapses today, we've got time.